This short video will look at carbon NMR spectroscopy. And as far as we're concerned, carbon NMR, carbon-13 NMR, will give us two major pieces of information. So the first thing, by looking at the number of peaks that we see in the spectrum, that will tell us the number of different carbon environments that our compound will have. The other thing, by looking at the chemical shift, so the position on the spectrum, that will tell us the type of chemical environment for a particular carbon atom. To help us with this, I think it's probably best if we look at a few examples. Here I've put the carbon NMR chemical shift data, and this will be included on your data sheet for any test or an exam. So you're given all of the chemical shifts that you'd expect certain carbon environments to give you. Let's start with a nice easy compound. So here's ethanol. See if you can spot how many different carbon environments it has. Well, hopefully we're happy that there are two different carbon environments, so they're not identical, those carbons. One is clearly in a carbonyl bond. Now see if you can find these carbon environments in the table on the left hand side. So the carbon that I've highlighted in yellow, the one in the carbonyl bond, is one of those. So we've got an aldehyde, and we'd expect to see a peak for that carbon around about 190 to 220. So in this region on the spectrum, whereas the carbon I've highlighted in green is one of those, so a carbon living next door to a carbonyl group, so we'd expect a peak for that carbon in the 20 to 50 region, so something like that. Let's look at this. So we've got an ester, it's methyl ethanoate. How many different carbon environments do you feel it has? Now you might be looking at this thinking it's got two methyl groups, so will this methyl group be the same as this methyl group? Hopefully we can see that the molecule is not symmetrical, so the methyl group on the right hand side is directly bonded to this oxygen, whereas the methyl group on the left hand side is bonded to the carbonyl group, which means that those methyl groups are not the same, those carbons are not equivalent, and hopefully we can see that the carbon on the carbonyl bond is also different. So we've got three different carbon environments, so we would expect three peaks for methyl ethanoate. Again, see if you can find where these carbons are on the table on the left hand side. The yellow carbon is a carbon living next door to a carbonyl group, so that's going to be one of those. The green carbon on the right hand side is a carbon directly bonded to an oxygen, as it says there, in an ester. And finally the blue carbon, so the carbonyl, so we've got two choices there, so we've either got the one for the esters and the acids or the aldehydes and the ketones. Hopefully we can see that we've got a carbonyl in an ester. So we'll see three peaks in those regions, something like that. Let's take another example. Here we've got a ketone, pentan-3-one. See if you can see how many peaks you think this will give us. Well done if you thought three. So we've got the carbonyl group in the middle, which is obviously different to everything else, but this molecule now has some symmetry, so the carbons either side are in equivalent environment, and the methyl groups on the end are also the same. So this will give us 3 peaks. Let's find where the chemical shifts will be for these 3 peaks. We'll take the yellow carbon first. So this is the carbonyl for an aldehyde or a ketone. So this is going to come in around about there. The green carbons, 20 to 50, and the blue carbons not next to anything particularly interesting, so down at somewhere between 5 and 40 parts per million. So that's what we'd expect our spectrum to look like. So 3 peaks in those regions. You can also see that the peaks for the blue and the green carbons will probably be higher than that for the yellow carbon because they've been caused by twice as many carbons. Let's now have a look at what a benzene might appear like in carbon NMR. Well, benzene on its own, all of the carbons are equivalent. We can see the region where we'd expect to see carbons in a benzene ring. So for benzene, from around about 110 to 160, we'd expect to see 1 solitary peak. Let's add something else to the benzene ring. And let's make it methylbenzene. See if you can predict how many peaks you'd expect to see from methylbenzene. Well, clearly the carbon of the methyl group is different to any of the other carbons, as is the carbon I've labelled blue, so there are no other carbons in the benzene ring the same as the blue one. Do you feel that there are any which are equivalent to the one that I've labelled in green? Well done if you picked the one to the right hand side of the blue. This yellow one is now different to the green, so it's further away from the methyl group, and that carbon is the same as the other yellow one, and then finally that carbon is different as well. So you can see that we've got 5 different carbons in methylbenzene, so we'd expect to see 5 peaks. The one that I've labelled purple would appear in the 5 to 40 region, but all of the others, the blue, the green, the yellow and the orange, will all appear in the aromatic region, so our spectrum will look something like this. Now let's see how adding a second methyl group next door, so here we've got 1,2-dimethylbenzene, how that might affect the symmetry and change the number of peaks. See if you can work out how many peaks this compound will have. So the methyl groups are clearly equivalent, as are those 2 carbons, and then those 2, and finally those 2. So now we've just got 4 peaks in our compound. 3 of them will be in the aromatic region, 2 down 5 to 40,